Okay, so today we're going to be working with our calculators, still using the same area formula from yesterday. We're going to be taking some time exploring one particular problem. So if we can turn to page 7. Okay, we are going to make the calculator do a lot of the work for us, but we do need to know how to set things up, and that's the challenge of the problem here is being able to set things up, and use the calculator to find the necessary information. So I took this. Let me read this problem first. It says, let R and S be the region in the first quadrant shown in the figure. The region R is bounded by the x-axis and the graph y equals 2 minus x cubed. So this triangle-looking region is region R. Region S is bounded by the y-axis and the graph of 2 minus x cubed. So this left region here, that's region S. I purposely made it so that we're finding the area in two different ways. Now, on the AP exam, you'll get to choose which one you want to do, but for practice purposes, I think this is a good exercise for us to explore all the ways of finding area to really get a good feel for how area works. So we're going to do we're going to find area of region S first. Okay. And we'll start with the easier one. Okay. We'll start with top minus bottom. Okay. Where we're thinking of the graph as above each other. So let me shade in region S. Now, we know our area formula. Let's see if we can just set it up here, and we can use our calculator to find it here. Area is a depth integral from where to where? What's the left bound that we see in the shaded region? It's the furthest left. Yeah, 0. And then the right endpoint is going to be wherever this what? Wherever the intersection is, right? And how would we find that intersection? Yeah, set equal to each other. We're going to make the calculator do it for us, but yeah, algebraically we'll set equal to each other. This will be hard to do by hand. We're going to make the calculator do that for us. So that will be our upper bound. We can fill that in a second. And we'll do top minus bottom. Okay. What's the top graph in the shaded region? Yeah, it's going to be this one here, right? Which is the 2 minus x cubed. And the bottom function is the what? Tangent x. Okay, so we see that, right? So it's 2 minus x cubed minus tangent of x.
Yeah, but the upper
not yet, right? We're gonna find that. We don't know what that intersection is yet. But let me draw a representative rectangle. Obviously, the real rectangle is going to be much thinner, infinitely thin. But this is the idea, is that these rectangles are going to extend from this side all the way to this side. We're just adding infinitely thin rectangles to accumulate them and find the area of the region. But we'll make the calculator do it for us, and we'll use calculus to do it as well. Okay, so now let's go to our calculator, see if we can find this intersection. And we're going to graph it, spend time graphing it. So under y1 and y2, y1, I'm going to put tangent of x. y2, I'm going to put 2 minus x cubed. You're going to do zoom. Let's do zoom 6 just to see where that lands. And we're probably going to do a little bit of zoom in to get into the region that we care about. So this is showing a little bit too much. All we care about is that little sliver right there, the first quadrant. So what I'm going to do is I'm going to do zoom box, zoom 1. And let me kind of show you what we're about to do here. So I'm going to go to zoom 1, which is zoom box. And then once I get to zoom box, I'm going to move the cursor until I blink the cursor until I reach the upper left corner of where I want my box to be. Hit enter once, and then I'm going to draw my box. And once my box is drawn, I'm going to hit enter again, and then it'll zoom in on just that portion. Okay, so zoom 1. And then we're going to move the blinking cursor to where we want our upper corner of our box to be. I think this is, have it somewhere up here. Hit enter. And then don't hit enter again until you see the box drawn out. So just use your arrow keys to draw the box. That should be the region that we care most about. Hit enter again. Pretty close to what we have right there, right? So now we want to do second trace. So on the board there, second trace intersect. Okay. So it says first curve. I'm going to hit enter on this curve. And then the cursor is going to jump to the other curve, second curve, hit enter again. Hit enter a third time, and it should find that intersection for us. Yeah.
So why whenever it does the zoom has an error?
Okay, yeah, I'll show you. Now go ahead and write the full order pair where that point is, because we're going to need that y value later on. The x value is not going to be.
I didn't really see the code.
Yeah, you got to draw the box first before you get enter. Yeah. Okay, so my order pair is 0.902 and 1.266. So I'm going to go ahead and highlight that. I know that the y value may not be needed right now, but we're gonna have to use it eventually. Okay, so what can I put as my upper bound for this region here? From 0 to where? Yeah, 0.902. Yeah. So I'm going from x sub 1 to x sub 2, furthest left to furthest right for my top minus bottom graph. And notice how all my equations are set up in the form of, you see how this is y equals? All these are y equals. Everything to the right of y equals is in terms of x, and that is what gets shown up here. We can't have a mixture of different variables here. Everything has to be in terms of x. Our expression in terms of x, our bounds are in terms of x. We can never mix and match. Okay, so if we see that we have x's here and y's here, that's a red flag. Something is not quite right. Everything has to be in terms of one variable that we see here. Now, the reason why I say y equals is because that's how the equation look on the left side. It's always going to be y equals for top minus bottom functions, but what you enter into your expression is going to be in terms of x. All right, so now let's just enter this in our calculator, see if we can practice doing that. I'm going to take advantage of y1 and y2 in my calculator. So I'm going to do math 9 from 0 to 0.902. Right now, tangent is holding my top function, or y1 is holding my tangent, which is my top function. I'm going to go to alpha trace y1 on the board there, alpha trace y1, which is holding my tangent, minus alpha trace y2. Now, if you want to enter it in, it's not wrong. I just wanted to kind of work as, if we can get comfortable with using or calling these functions when they get more complicated, and if it takes longer to enter them in, it saves a little bit of time.
How do you get the antiderivative integral shell again?
Math 9.
Math.
Oops, sorry. I think I. Oops, my bad. 2 minus x cubed is first. So I have tangent being y1. So I need to swap that around. So my y1 is holding tangent. My y2 is holding 2 minus x cubed. So I need to flip this around. Should be y2 minus y1. And again, we know that we're off if we get a negative answer here. Okay, 1.161.
Do you go out again? Is there a good one?
Yeah, if you go to on the board there, alpha trace y1 or y2. All right, any questions with this? This is the easier of the two methods, but it's good for us to practice the other method as well. Sometimes we're forced into a problem where we have to do right minus left, and it's good to kind of get all those kinks worked out before we're forced into those types of problems. Okay, so any questions here? What do you see? All right, so number 2 is a little bit more involved here, but it's a good one for us to practice with. We're going to force this into a right minus left curve here. So again, shaded region is S. But now, instead of adding infinitely thin vertical rectangles, we're going to add infinitely thin horizontal rectangles. And whenever you see a horizontal rectangle, you know that we have to make some adjustments with our equation. So imagine sliding this horizontal rectangle up and down this region here. Is the left endpoint of this rectangle always hitting the same graph? The left rectangle is, right? It's always hitting the y-axis. What about the right endpoint? Is the right endpoint always hitting the same graph? It's going to suddenly change after this intersection, right? So initially, this is, if I slide this from down here, initially it's hitting what? Which graph?
Tangent.
Tangent. But then after this intersection, it's going to start hitting what? The 2 minus x cubed. So what do you think we need? Can we rely on one integral notation? We need 2, right? Because we have a different relationship here. The right curve in this region is different than the right curve in this region. Okay. But if we want to do right minus left, everything that we have to put in has to be in terms of what? In terms of y, which means that our equation is not going to be in the proper form. We're going to have to do some work to get there. Okay, so if I want to solve for x, right now this is tangent of x is equal to y. If I want to solve for x, what has to happen? This tangent will turn into what? Inverse tangent. So x equals inverse tangent y. So I'm going to highlight that. Inverse tangent of y is over here. And then if I want to do 2 minus x cubed, I need to solve for x. So let me swap the x and let me just add and subtract so that I'm not dealing with a negative x cubed. So what if I did this here? X cubed plus y is equal to 2. Just rearranging it. I have to get it into x equals if I want to do right minus left. The y equals is perfect for top minus bottom functions. But for right minus left, everything that I insert into my integrand notation has to be in terms of y variable. Okay, so if I want to solve for x, what can I do here? X cubed equals what? 2 minus y. And if I want to get x by itself, I can take the what? Cube root. Or if you want to write it as 2 minus y to the 1/3, that's fine as well. It's up to you. They're equivalent. So this is all in the proper form. X equals inverse tangent. X equals 2 minus cube root 2 minus y. What is the equation of the y-axis? What is that equation? X equals 0. So you see how they all have a similar form that we need? They all will take on the form of x equals 0, x equals the inverse tangent of y, x equals 2 minus y to the 1/3. And then everything on the right is what we're going to be inserting into our formula. So we need two separate integrals here. Okay. We need the lowest y value here to this y value, which we have, which is 1.266. And we also need the y value here. How can I find the y-intercept of this 2 minus x cubed? Yeah, y-intercept is when x is what? 0. So if I plug 0 in for x, y is equal to what? 2, right? You can use your calculator, you can, but I think it's easy enough where you can kind of just look at it and tell that it is 0, 2. And again, this is 0.902. I know I don't need the x value, but I just want to go ahead and write the full order pair here. All right, so this is a little more difficult here because we have to set up using two definite integrals in terms of y, but we should get the same answer. We're talking about the same region here. Okay, so let's follow the formula here. y1 to y2, we have to pick the lowest and highest y value in this first region here, where this rectangle is. What's the lowest y value that you see in the lower region? 0 to what? 1.266. Good. All right, let me highlight that in red. So I want to make sure that we really see that this is two separate regions that we're having to break up here. 0 to 1.266. Right minus left. What's the graph on the right? Well, we got to rewrite it, right? What's the adjusted equation? Inverse tangent of y, okay? Minus, right minus left. What's the left endpoint of my rectangle touching? What's this equation here? 0, right? Right minus left. The right endpoint is sitting on the curve. The left endpoint is sitting on the y-axis. Okay, so whatever the calculator gives us for that, that will be the area of the bottom region. Okay, now let's move on to the upper region. So from where to where? Good, 1.266 to 2. Okay. Okay, again, we're going to do right minus left. Let me highlight using a different color here. what's the right endpoint of my upper rectangle touching? Good, root, cube root of 2 minus y, or 2 minus y to the 1/3. Right minus left. The right endpoint is at the cube root. The left endpoint is sitting on the still what? 0, yeah. Okay, now we're not going to be able to graph this, but we don't have to graph it, right? We already know what we need. We already pulled it from the graph. We just have to be able to enter this in the calculator. But the adjustment we have to make is instead of putting y's in our calculator, we have to put what? X, yeah. So this one, I would just go ahead and enter directly into the line here. I mean, we're not going to be graphing it, so I don't think it's worth the trouble having to put in the y1 and y2. And we'll say 0 to 1.266. Inverse tangent of x. I know it says y here, but we got to do inverse tangent of x. So second tangent of x, close parentheses, dx, plus, and then math 9 again. (1.266) to 2. Cube root. So if you do math 4 will take you to cube root. We get the same answer, right? We should, because we're talking about the same area here. 1.161. Okay, this is the hardest part of this unit. Being able to go back and forth between x and y, knowing how to do, especially right minus left rectangles. This is what students are struggling the most with. If you can get this down, then volume will be a breeze. It's the same concept. We just have to adjust our formulas a little bit, but this is the hardest part of our unit. Students can do top minus bottom, but right minus left poses a more difficult challenge.
You need to know how to do both, right?
Yeah, I need to build both because some right now we're picking problems that we can do both ways. We can kind of compare it and actually see that distinction, or be able to see the comparison. But there are problems, especially with volume, where you're forced into one particular formula because the other one just doesn't work. So it's good for us to kind of get. I mean, obviously, we will always want to prefer this, but if we're forced into this, we need to know how to do it. Okay. Yeah. Questions? Yeah, so we do math 4. Okay, let's do part B. Now we're looking at region R. In region R, we're also going to do top minus bottom and right minus left. The good thing is that we've gathered a lot of information already from 1 and 2, so we can reuse a lot of information that we've already gathered from these first two. But any questions here? This is a big big topic here. So if you're have any questions, let me know so I can clear anything up. And obviously, we'll get a lot more practice with this, but I want us to at least feel like we understand how this works. Okay, let's look at number 2. Now we're going to do region R. Let me lightly shade region R. Okay, we're going to do top minus bottom first. So we're going to force this to be vertical rectangles. But if I draw a representative vertical rectangle here, and imagine sliding that vertical rectangle left and right, am I hitting the same graph every time, no matter where I slide it? What's going to happen? There's a change in what? Top graph, right? If I slide my rectangle over here, I'm hitting a different graph than over here. And there's going to be a change at this intersection. So we know what the intersection is, right? Which we've already gathered. So 0.902 and 1.266. Let me write that there so we can just reuse it. All right, let's see. So how many integrals do we need if we want to find the area of region R? 2, right? So let's do the left region first. So depth integral from 0 to 0.902. Top minus bottom. What's the top of my rectangle touching? Actually, okay, we can go back to these original equations, right? Because top minus bottom, we can use the original equations. There's no need to adjust for doing top minus bottom. So tangent is my top. Okay, what's the bottom of my first rectangle touching? Y equals 0, right? 0. Now look at the form of all my equations here. Y equals tangent x, y equals 2 minus x cubed, y equals 0. Every equation that I'm using has the same form on the left side. They're all y equals, and I'm just inserting what I see on the right side. We close that off with dx. All right, second, I start where? 0.902. And this endpoint is the what of the 2 minus x cubed? Is the x-intercept, right? So x-intercept, we have to use our calculator here. I mean, we can solve it. We can solve for x and replace y with 0, or you can go to your calculator and do second trace intercept and find that x-intercept. I'm going to just do it by hand, but well, we can do both. So if I replace y with 0, because this is when y is 0, right? So cube root of 2. But you can also just go to your calculator. If you want to find that x-intercept, you can also do second trace 0. 0 is the x-intercept. And then you can pick a point to the left of the x-intercept, hit enter. Scroll to a point on the other side of the x-intercept, hit enter. Hit enter a third time. 1.26, which is the same thing as cube root of 2. So okay, so we're in the second region here. Top minus bottom. What's the top of my second rectangle touching? 2 minus x cubed. Top minus bottom. What's the bottom of my second rectangle touching? 0. Okay, so entering into our calculator. Okay, that's my first integral. You could do math 4, which is cube root of 2. 2 minus x cubed. .729. Okay. Next up, we're going to find the same region R, but we're going to do right minus left. So let me shade in region R. And let me draw a representative rectangle so I can just visualize it moving up and down. Okay, so imagine moving that rectangle up and down the shaded region. Is it hitting the same graph no matter where we slide it? Yes. So there's no need for two integrals, right? All we need is one integral because there's no sudden change. It's consistent all the way through. But if we want to do right minus left, our equations has to be written in what form? Yeah, but we can just carry them down, right? We've already built them from above, so the intersections, everything is ready for us to use. So in a sense, this is the easiest one because we already have all the information that we need to build our area here. Okay, so if we're doing right minus left, we're sliding this rectangle from the lowest to the highest y value. So depth integral from lowest to highest. What's the lowest y value? 0. What's the highest y value of my shaded region? No. Right minus left. The right endpoint is sitting at the 2 minus x cubed, but this is what's the adjusted equation for that? X equals what? Cube root of 2 minus 1. So that's the one on the right. And this one here, the adjusted equation for tangent of x is x equals inverse tangent of y. Okay, this is what you're going to write down on paper, but in your calculator, you're going to use variable what? X. Okay, let's try that. Math 4 to get to your cube root. Make sure you close your inverse tangent of x with its own set of parentheses. We should get the same answer, 0.729. Okay, got one more calculator problem for us. Let's go to page 8.
You know, you're gonna ask why one method, right?
Right. So area, for the most part, you can choose which method you want, but the right minus left is going to be really important for later on. So it's good that we know how to do it. Okay, let's look at number 8. Sorry, page 8, number 2. All right, so let R be the region bounded by the graph y equals e to the 2x minus x squared. So that's going to be this whole curve here. This curve is the exponential e to the 2x minus x squared. There's a horizontal line y equals 2. And there's a horizontal line y equals 1. So we have 3 graphs here. You got the curve here, and you got 2 horizontal lines. Find the area of R. So if I want to find the area of R, we just do top minus bottom, right? What's the top of my rectangle touching? But what graph is it touching? Yeah, the exponential function, right? What's the bottom of my rectangle touching? Y equals 2. Okay, so we know that's the formula. It's going to be the exponential minus 2, but we do need to graph it because we do need to find these intersections, right? So we don't know where these boundaries are. So let's do that. we're gonna erase y1, y2. And I'm gonna do e to the 2x minus x squared. Y equals 2. I like to do zoom 6 just to see where I'm at. It's really small. So I'm going to do alpha zoom. I'll do zoom 1, zoom box. I'm going to draw a box around that region there. Hit enter. Okay. Don't hit enter again until you see the box drawn. So use the down arrow to draw the box. Okay, so now let's do second trace intersect. Let's do find the intersection of that left endpoint first. So enter, enter. I get 0.446. My first intersection. So do second trace again. Scroll over to a point closer to the other intersection. Hit enter, enter. 1.553 or 1.554.
You rounded it up.
Yeah. Mm-hmm. Okay, so we can say depth integral from left endpoint to right endpoint. Top minus bottom. The top is sitting on the curve. The bottom is sitting at the line. Okay, math 9. I have y1 holding e to the 2x, so I'll do y1 minus y2. .514.
Oh, we label it if you don't give us any units.
Yeah, if this doesn't give you any units, you don't have to label it. Yeah. But if we just understand that it's area here, we can kind of just remind ourselves that it's units squared. Whatever the units is, it's the area. Yeah. I'm sorry. Yeah, do zoom box, zoom 1, and then you can move the cursor to the upper corner and draw your box. Okay, now part B. Find the area of S. There's two ways to do it. One way is going to be a little bit easier. But let's explore that. What do you think we can do to find the area of region S? So the more straightforward way that's actually more difficult is, what if we think of it, I mean, we could think of it as 3 separate regions here, and do the area of this, plus the area of that, plus the area of this, and that will get us our area. But is there another way where we can find region S? That can be a little bit cleaner.
You think you use the area from previous problem to do something?
Okay, and how would you reuse that?
Or never mind. Maybe you can like subtract it, like the exponent, like the 2x intercepts, like for the first problem, like 1.5 by 4 minus 6. And it gives you like the.
Okay, yeah, you're on the right track. So what if we found the area of the entire region, RNS? So what if we found the area of this together? How would we find the area of this? Like just completely ignoring this 2 here.
You add the like your first problem to.
Or we can just think of it as, yeah, exactly, right? We find the area of this region and subtract R, and then what's left over is region S. Yeah, so here's the idea is that so we completely ignore 2. We just find that entirety of that region. This is going to be R and S combined. If we find that full area and then we subtract R from part A, then what's left over is this middle portion here. So we're starting at 0, but we do need to find out the intersection between the curve and the line, y equals 1. So I'm going to erase that y equals 2 here. I already know that's going to be 0. I'm going to find this intersection between the graphic 1 and the curve here. So second trace 0. Oh, sorry, second trace intersect 2. Okay, so it looks like it lands right on the whole number there, x equals 2. Okay, top minus bottom. The top is the e to the 2x minus x squared minus 1 dx. So whatever area that we get here, we'll take this, subtract the upper portion at R, and then what we're left with is going to be region S. All right, so your homework, still from 7.1, from the same pages that you did yesterday, just 25 to 31 odds. All right, come get your phones. When do you want to come? I think your lunch. Okay, that's good. All right. Thank you.
Thanks for waiting for some results to come out, you know?
Yeah. Oh, you're just waiting right now?
Yeah.
Nothing you can do, right? Just
Yeah.
This.
It's nerve wracking.
Yeah, but.
Gonna battle this too. It's gonna be actually good.
Yeah, I understand.
Starting to hit me like a brick wall. Did you have